initial workshop on recommender systems starting later this week. Pretty sure in person is sold out, but there is still a spot available for online. So if you like what you hear and you want to hear more, make sure to register for the workshop. And also ask me if you want extra discount since you're awesome and you're here. All of you.
Okay. Okay. Hi everyone. First of all, thanks for having me. I'm really happy to be here. It's always nice to be part of this group and to talk, and thanks to Drop for having us. So today I want to talk about like our approach for the recommender system, the RecSys competition. So you guys know what RecSys is? So RecSys is this conference that it happens every year, and every year they will have a different challenge. A couple years ago it was Spotify. It was a Spotify challenge about how to recommend the song given certain conditions. And this year the competition was about Trivago. That was basically a question about how to re-rank a list of recommendations. And we should talk a little bit about why the question in itself is important. Why would you want to re-rank stuff? Or how to measure, like if you're ranking, if it is a good ranking or not. But before getting there, I need to start like first introducing my team. My team is quite awesome. I love all these guys. They're amazingly good. So we have Max. He's our CTO. Anson, he's a team short of like, I don't know, I will call him feature master, feature Jedi, something like that. We have Joy, Ilya, and Ishao. All of them contributed, including myself, to this competition. So every year they will have the competition. Many teams, I think this year was like 750 teams or something like that participated around the world. It's a really fierce competition, and we're really happy to participate. We participate every year, and it's tons of fun, but a huge amount of work. And if there's something that you want to know about the competition or how to compete in Kaggle or these kind of things, it's mostly dedication. You need to spend a lot of time trying out stuff, failing, trying out stuff, failing, and it takes a lot of work. Okay, so have any of you used Trivago? So Trivago is not that really popular here, but Trivago is like another version of Expedia. Actually, if my memory is right, Expedia owns Trivago. So basically what they're going to do is you're going to look for some place, say Toronto, and you want to check for some hotels, and you want to see like what is a good, I want to stay, say, from September 15th to September 16th in Toronto, and this is what it will show up. It's just a typical search, aggregated search of many different websites. So you will see that some of them correspond to Booking.com, some of them will correspond to Expedia, another one like says TownUp or something like that, I don't know. So they will have just many different options, and the way that you see is just how the system internally, Trivago system, will rank the hotels, right? So it's just showing you the hotels in the order that it thinks that it will be the most relevant to you. The same thing that Google does when you search for anything. Now this is pretty cool, okay? You can see that you can actually modify your searches. Like once you search for something, you can always say like, oh, I didn't want to go to Toronto, I wanted to go to Mississauga. I want a point of interest, I want to be near downtown. I want to filter by price, or I want to filter anything that has at least 20 mirrors in the room. Or you want to sort. Like it's just conditions that you can put in order to make your query more relevant to you. Notice that small sentence actually has a lot of meaning, because basically I'm saying that these things is how you are personalizing the search criteria towards you. And that will be an important component later, because whatever ranking you want to offer the users is the best ranking associated to the user. So you want to personalize this thing. So let's see, how does I'm going to call this thing items, and I'm going to call the feature that is, this is rank 1, this is rank 2, and so on. We will have at most 25 ranks. So in every item will just look like this. You should notice that there are a lot of information associated to the item. We have information where it will just tell you like the description of the room and stuff like that. There will be some photos, some reviews, and some deals. And these are actions that the user can play with. You can just click and everything looks really nice. You can go through the pictures and you can get some information. Quite normal. Now, how do you think Trivago makes money? Or at least how I think they make money? Huh? Yeah, so like maybe some commission, I will guess, but like it's actually, there are two kinds of commissions. There is a commission for sale and commission for click, right? So the actual way that they get money is like if the user clicks in the associated website, right? So what they want to maximize to some extent is the last click out. When they say view deal and they go to the other website, we're going to call that action a click out. So you're clicking to go out to the other website, and that's the most important thing we want to measure. We want to measure how the company is going to make that more efficient. But like, if I see a bunch of stuff, if I go over the first 5, 6 stuff and I don't see anything that I like, then I may not use the website that much. So it's better if I see things that are relevant for me on the top. So I click out on those, so Trivago can get more money. So they will be interested in maximize the click out. So I was mentioning before the ranks are associated from 1 to 25 at most, and then the items have some information. So if the important thing for us is the click out, and we understand that the business model is to have the click out, the things that are more relevant for me on the top, how do we measure that as a good ordering or not? So there are many.
Just out of curiosity, does it have a concept of promoted links?
So I don't think they may do, but it was not part of the data set.
Okay.
I don't know if they do. I don't remember seeing it. Yeah. So how do we measure the quality of the ranking? So the quality of the ranking is really simple. So if the thing that the user clicked out at the very end was on the top, then my ranking was really good. I offered in the first place the thing that the customer wanted. So I should get a score of 1. I'm getting 1 point. If it was in second place, that's still pretty good, but I'm only going to give you half point. If it was in third place, I'm going to give you 1/3, and so on. So if the thing that the customer wanted at the very end was in position 25th, then I'm only going to get a score of 1/25, which is really low score. So for each user, I have that criteria, and not even for each user. For each session, I will have that criteria, and when I go over, and then I take the average over all those scores. And that is called the mean reciprocal rank. It's just a way to measuring how accurate were you at giving the best recommendation. Okay? Any questions so far? Does this make sense? Yes?
Is that for every user or is it global?
For every session.
Okay.
So that will be the metric we are going to use. Users may have many sessions, but actually for the purposes of the competition and everything, the only session that matters is the last one that the users have. That's how it will be measured. We'll talk a little bit more about that in a second. Yes?
Does the session end after click out?
Not necessarily, and that will also show up in a second.
How do you aggregate the rankings? So like, let's say you have a ground truth, or like, is there any ground truths at all?
Yes, the ground truth will be the last click out that the user has. So we will see when we talk about the data in a second.
I think what you ask, the rank is the presentation of each hotel,
Yes.
and the click out, the score is which rank you click on.
Yeah, so let's
If
say,
you click on item 35, it's rank 2. So it takes only rank 2 to the measure.
And what happened?
one half. If they click on it, it should be rank 1.
If they click in the top one, then they click in rank 1. They click in the second item, they rank in rank 2, so they get only 0.5. And so on, but that's only the last click up.
Is there any particular reason why they didn't use normalized discount?
So like this is,
That's second point.
Okay.
but like,
Yeah,
that has an
it's-
easy answer because that has nothing to do with us. That's what Trivago chooses. I can give you many reasons for that later, but like, yeah. So, okay. So the goal is, so we have a ground truth. We know where everybody ranked, but it may have been better if the rank that we have offering will be different. So the question here is, given the current rank that they have, can we find a way to re-rank this thing in such a way that was better or more personalized for each user? So this is not a question about like how to find the rank from the very beginning. It's a question about like given some ordering, how can we make it better? Okay? That will be the whole competition. And we are going to measure better by using mean reciprocal rank. Good? Okay, so like if we don't do anything at all and we just give exactly the same order that Trivago gave us, the score that you will get is 0.5152. You don't have to do anything and you get that for free. If you only recommend the top popular, if you sort by popular product, I think the score is like 20 something, 0.20 something. So popular is not the best. The best one we have so far and our benchmark should be just doing nothing. Okay? So let's talk about how the data set looks like. The data set basically comes like in a data frame, really standard, where we have different kinds of features. So there is a time component. Oh, that will be in the next slide later. So there are about 900K training sessions. And you will have that the sessions basically looks like a timestamp when something happens. Every time that you go to the web page, you begin clicking and doing stuff, that will be called a session. And every action that you do will be called a step. So you click, that's a step. You filter by whatever, then that's another step. You look at the pictures, that's another step, and so on. You have the reference, that is basically the hotel that you're looking at. You will also have the city that you're looking at and the current filters. And some information associated to the user, that is the device, the session ID, the user ID, and that kind of stuff.
So
okay.
Are all the features in the data set?
Yes, all these features will be there.
Before the engineering?
This is before engineering, yes.
Mm-hmm.
Actually, this is just one set of it. The reference is, for example, I should have a better example here.
Yeah.
It may be like, for example, the filter that you're acting, like what kind of filter is it, or like the point of interest or that kind of stuff. Okay, that's the reference. It's associated, like for example, interaction with images, I'm looking at this image. Sorry, I'm looking to the image of this hotel. Okay.
Just to confirm on the understanding, if you're saying that every time there's an action, the step changes.
Yeah.
So the timestamp will have to be given.
Yes. So like.
As we have multiple steps for the same times.
Yeah. This is a typo. This should be larger than this one.
I'm sorry, not the timestamp, but the session ID. There was something like that.
There is a session ID.
So that would have duplicate values.
That will have what?
In case if you have that in the data set, do you have duplicate value? You expect duplicate value?
No, like the data set is supposed to be clean. It wasn't for certain technical reasons, but it's one of the cleanest data sets I have ever worked with. It was extremely, really well parsed data set, and I was really happy to play with it. Like I didn't have to worry too much about how clean it was. Yes.
And can you have multiple click out in one session?
Yes. So actually, this happens quite often. So like, but it doesn't really matter. We want to predict is the last one. The last one is the only one that counts. Yes.
How many time steps does the data point have?
Is like we actually look at many of these distributions, and it's absurd. Like it can go from 1, where people just click in the first thing that they see, to 1,000, where people just keep scrolling through the same features. I don't know what they're doing. Yes?
Why is the last one the one you're trying to optimize?
Because in the last one, you are assuming that the customer is done.
Either way.
Click out will be much.
Yeah, but like that's by default, but like you suspect that the customer is happy and he was done. Like he found what he wanted.
The chance of having a click out is most probably in the last session.
Sorry?
The chance of having a click out is most probably in the last action.
Yes, that's usually the case, but it's not always the case. There are many sessions that don't have a click out as the last action. They were playing with pictures and they just closed the session. Any other question?
Just to be clear, so this session ID with that user ID, it can have multiple item IDs in there.
Multiple what?
Multiple items that they looked at within
Yes.
this. Okay, but what happens if 2 steps are for the same items? Does it just, the reference only changes?
No, like you can see the same image. You can see many images for the same hotel, so the reference will be the same.
So the reference is technically the item ID in here.
Is the item in which the action is going to be.
Okay.
But like sometimes it's not an item, sometimes it's like the filter that you have or things like that.
What happens if you click on the next page and see the next 25 hotels?
That doesn't exist for us.
Okay.
Any other question? Good. So There is another set of data that we will have that is for every hotel, for every item, we will have a lot of like properties, a lot of like the metadata associated to this thing. So like if there is satellite TV, if there is a swimming pool and whatever, whatnot, like all the information that you see when you go out and book for a room. Okay, so that's the metadata, and this is how typically the data set was given to us. So it was given as a whole training set that will actually correspond to the information at the beginning of November of last year, the first week of November. There were 7 days. There were 7 days, and the testing will be the day after. So this is off time. So like basically, and as we want to remain off time, we choose a splitting that is off time. So basically, we split forward in time because we want to preserve the same structure that the data was given to us. So notice also that this is what happens. Sometimes you have one user, and then they will have some sessions, and then the last thing that I care about is always the last click out, even if they have click outs before. Sometimes there are actions that are non-click outs, and other actions are click out. That's basically how the data was distributed. Another thing is like for training, we use about 100K sessions. For validations, about 80K. That's basically in reading the slide. Yes?
And for the same session, people have multiple steps, so you always take the last.
Always the last step. Okay, so now it comes to the really interesting part. Ranking is an extremely difficult problem. There are many losses and many techniques for doing ranking, and there are different techniques like pairwise ranking or things like that. They don't always work as you expect. Even though these things are totally designed for one task, sometimes other approaches work better, especially if you're able to change the framework of how you are thinking. One of the ideas that is crucial for our work was like, we don't want to think this as a ranking problem. We want to think of this as an item is going to be click or not, which becomes a binary problem. Notice the switch on mindset. Now I have a list of 25 things, and what I want to predict is this the item going to be click or not? Changes completely to binary, right? So from my list of 25 things, now my targets change. Is this going to be click or not? Totally binary. So the problem now becomes like, I just need to create a bunch of features to determine if this will be true or not. And then you may be asking, okay, so you find that and you find the likeliness of this item to be click or not. How do you sort them? Well, you can just sort them by the likeliness of being click. And now you have changed a ranking problem into a binary problem, and for inference, you just rank according to the likeliness of being click. This is the most crucial thing one of the most crucial things. There will be some other things that were quite interesting along the way.
Really amazing.
Yeah. Really? That was our CTO. He's a Kaggle Grandmaster. So, okay. So the question then becomes a feature generation problem. Like in real life, you need to create features. You need to be smart about creating features, and that's extremely hard. I like thinking feature generation as, reverse engineering how the user thinks, or why the user is behaving the way they behave. So in order to do that, you need to begin to, you actually need to sit in front of the Trivago web page, go through the Trivago web page, pretend that you're a user, come up with features associated to those things, and meanwhile you're doing that, make sure that you can translate whatever you think your intuition is telling you, being able to translate it to code. And that is hard. And it takes practice and skills. And that's where Anson was excellent. He was amazing. He will spend hours in front of the Trivago web page and come up with things that will completely put us on top. Okay, so let's see how you create features and what kind of features we found that were kind of relevant. So some of the features that we divided our features in 3 or 4 groups, I don't remember, so let's see. Some of them are really simple. They depend totally in the context that you are, right? So the device use, right? That's something that's really simple. They come just from your session. How many steps were in the session? It just happens in every session. The time of the duration. How many actual actions that weren't looking at, that weren't related to the item did you do? How many were related with the item and that kind of stuff. It's things that are global within the session.
What is number of non-item actions?
So there are actions that are looking at images. Those are item actions. But there are actions that are like filtered by this. This is non-item because it's not associated to a single item.
When you're calculating your features, this is within sessions, or are you looking
Yes.
at the steps within the session up until that point and predicting the next?
Because we separate all our session in everything that happens before the last step and the last step.
Oh, okay.
Because we only care about the last step.
Okay.
Okay, so these are the typical context-associated features that you can create. Those are the simple ones. Before I forget, and I'll tell you later. That was something really amazing. Okay, but then you say like, okay, counts are really nice and all that kind of stuff, but you can get the statistics. So this is where it becomes a slightly item session. It becomes slightly interesting. So you can actually begin associated information to each of the possible items, right? Like for example, every item appears with certain rank across all the different sessions that exist, right? You can predict, for example, what was the mean rank that this item has had across all the sessions. You can get information like that. Like you can also think of the rank associated in this case given by price instead of just the rank that they were given. So because people usually prefer cheaper stuff when they are spending money, but depends on the person. In any case, so like you can associate also the mean of that rank and that kind of stuff. You can also find out how many actions are there associated to an item, right? Like across all the sessions, how frequent is that this item was interacted with? How long people spend in this item?
Excuse me. All these building feature to flatten the session, right? To one row. That's
Yes.
what we do now.
Yes, that's actually an important thing. One of the most important things for iterating is what is the favorite programming language for data scientists?
Python.
Don't use Python. So our code was extremely fast and it has a lot to do with Java. So like all the process of feature generation in Java, it took us like, I don't know, 3 minutes. Like if you write that in Python without using multiprocessing and things like that, it will take much longer. Even with multiprocessing, no, we weren't able to match Java.
So, do I understand correctly that your feature engineer generated about 300 features?
Actually, more. We generated more than thousands of features. The ones that we selected and were the best were 300. But like, I think even when we were putting, like the problem at that point, like generating features, we could generate 1,000 features in relatively short amount of time. The problem was the SG boost later. It will take much longer to compute.
Can you recall, for example, some feature that sounded ridiculous to you?
Really what?
That was ridiculous, just because I cannot imagine 300 features like obtained from
something that is really close?
Yeah, or absurd, like because 300 features is a lot.
Oh, I see. You will find out that it's not that many. Mm-hmm. Because every time that you have like some sort of distribution, mm-hmm. you can associate several things to that distribution. Okay. Like the mean, variance, median, that kind of stuff.
Oh, like
you can also have relations between features, co-occurrences. So this thing begin exploring really fast.
And how do you get item dwell time? Item dwell time
is how long did they spend in that time, in that item.
But then, when they click and then they open the page of that specific.
No, when they interact with it, like looking at the pictures or things like that.
Alright, so and for choosing those 300 features at the end from thousands, did you use any specific feature selection method or just AISC boost like feature importance?
Neither.
Rank them?
No.
Like
we
how
just
did
keep
you
trying.
choose? How did you choose the 300?
We keep trying.
I know, like what was your metric like?
Is it increasing our results or not?
Because it's like 100.
No, because we didn't.
factorial.
We weren't. It's not like we have 1,000 features and then we come down to 300. No, we have 300, and in order to add a feature, it needed to add to our score. So many features that we create, we didn't use because it wasn't adding to the score.
So there is, if you look at this section of the paper, there's the percentage of the thing of adding a new feature, and that's how the importance rank.
But like, yeah, like it's not that we created a lot and then we chopped down a bunch. No, we started with a few and we were only adding the ones that were helping us. We usually, like if something was helping, we usually didn't take it out. Yes?
So you create your feature in Java, but you train your attributes for in Python.
No, in Java.
In Java too.
Actually, most of the times we're done training it in C++. Yes, so if we were using Python to train the SGBoost, no, we were using either Java or C++.
Another question is about basically a little bit about your transforming your rank over to a binary classification problem, because you are session-based problem. I'm just a little bit of concern about the violation to your ID assumption, because if you're session-based, basically clearly your model is the ID assumption.
Sorry, I don't understand the question.
So basically, if you train a model on the session-based, right?
Yeah.
So each samples are not independent anymore.
They are independent. I mean, they are not totally independent.
It's definitely something.
But like we don't care about the sessions anymore. We translated the problem like everything is associated to an item. Like now you have the item, and associated to this item, I have some properties. Some of the properties of this item is it belongs to this session. So now the session becomes a property of the item. So you can create features associated to the session that become properties of the item. All the items will share the same properties that are obtained from the session. But the item itself may have some other properties.
So the item is your sample?
Yes, basically. Yes?
Now it's about the properties metadata.
Yeah.
For each item there is the properties.
Yep.
In the one that encoding or never mind.
So yes, that's one way that you could do it. We did it that way, and we tried to do also. I don't remember if
it's only for one item. And you're going to flatten the session. So what? You sum it, all the properties, all the ones.
Yeah.
For all the items, or some moments.
No. You sum for every item. There is the properties that the hotel has. And then you can have a one hot encoding associated to each of the properties. Basically, this is counting how many properties it has.
So all the session we just count the properties.
Yeah, that's one way, but like we actually obtain more but that's just an example.
One confirmation. So if you go back to one of these slides, like the previous slide to this, where you were saying there are 832,000 sessions in training split. So is that with the unique count of the sessions? Because then later in the video it says that there are 14.5 million instances.
No, that's not the unique counts. Like remember, we only care about the sessions that the last item was a click out. The sessions that the last step wasn't a click out, we discard. We didn't use them.
So 830,000 are only but ones with click outs.
Yes.
Then how does it go to 14.5 million instances?
Remember, each session has 25 items.
So you just split it in by items and then.
Yeah. Because right now we are changing to a binary problem, right? So now you have more samples per session.
Could you quickly summarize that question again?
So basically the question is like if we have this number of sessions, how is that you have more training data? We have more training data because each session gives about 22, in average 22 points of data, each of them associated to an item. Okay? With the maximum being 25 and the minimum being 1. Yes.
The user IDs and the item IDs, how did you use that? Like, was it one-hot encoding or?
So we'll go over that later. I think so. If not, I will just mention. So we were in item statistics, but also There are global statistics, as I was mentioning before, like what is the usual rank that this thing shows up, what is the average rank. But more interesting, now that you have global information, imagine that the average price rank is 5 for this item. But in this particular case, I'm ranked first. So that means that there is a relation between what happens globally and what happens locally. If you want your model to know that there's that relation, you can just add the difference between the two of them. That's how you begin combining global information with local information. Those kind of features are by far the most powerful that you can create in general. When you combine global statistics with local statistics, that teaches the model how to go from the generalities of a general user to the personalization of a user, because it's telling you the difference between the global setup and the local setup. Okay, so I don't have it, so I'm going to tell you. So like users, most of the times you don't encode the users like that, neither the items. We try a couple of things that way, they didn't work for us. We also tried creating embeddings for them, they didn't work at least in this part of the model, it didn't work. So we weren't able to do that much. So what we ended up doing is like counting co-occurrences, and that was more helpful. Like how many times does this user interact with this item kind of stuff. Okay, so impression aggregations. So this is slightly more interesting. Like sometimes you want even to localize even more. If you have a session, you have the local information associated to the item, and you have the local information associated to the session. But you may want local information associated to the neighbors of the session, as neighbors of the item. Let's think why that should be relevant. You are scrolling down in a web page or on your phone, right? How many items can you see? 3, 5? You cannot see the 25 of them, right? So that means that the things that the user is seeing at that moment is just the neighbors. So maybe I should compare the item that I have just with the neighbors. You will only learn those things if you interact with the app. Like that's the kind of things that is, again, you are reverse engineering the user. You will only be able to understand those things if you are playing with the thing that we're supposed to be playing with. Okay? So that's how we obtain these things. So you obtain the mean of those things, the statistics along those things, and that kind of stuff. And that's going to move on. And then you need a model. Yes?
You didn't use the search characteristics, what the search was, because of which you had the you got certain ranking of hotels.
Say that again, sorry.
So the user would have searched something because of which you would have got the rank ordered list of hotels.
Yes.
Right, I'm saying like you didn't use the search, what was searched?
So like we were given already the search. So we don't have the first step of like when they enter something, we don't have that part. Okay, so then next is the training time. Like we created a lot of features, and the reason we created a lot of features is because we wanted to use something really powerful that exists out there that is called SGBoost. We really like SGBoost. SGBoost is like one of these things that is extremely good, but particularly hard to understand. How many of you understand how SGBoost works? Completely. If I tell you this hyperparameter, will you be able to tell me what it does? So SGBoost is really hard to understand, and not only to understand, actually to deal with data. And to train, like, you need to do a lot, you need to do a way of doing hyperparameter search, that kind of stuff. But the advantage is that in general, you can train really large amounts of features, all kinds of features. You can have numerical, categorical, you can have whatever you want, and it will be able to process that information well. So like you don't have to do a little feature processing, and it's also something that runs relatively fast. You can train an SGBoost model, a small one, for this thing with 330 features, I think in 4 hours. A large one takes much longer. It also uses multiprocessing. Actually, we also, right now, even has a GPU version that we use a lot. So the GPU version is like, I think it was 80% faster for us, but it had a problem with the random seeds that I think they corrected since then. So we play a lot with it, and we were training always we always have at least 5 models training among all of us. So it wasn't just one person training models, it was all of us training models all the time for several months. Okay, so that's why we use XGBoost. And here is some things that you can get with that. So now as we change our particular problem from a ranking problem to a classification, from a binary classification problem, we want to change the metric that we are using. Instead of using MRR in order to know if we were doing well, we were going to use another proxy that will be AUC. We found a high correlation within higher AUC usually corresponds to higher MRR for us. Furthermore, every increase in AUC will correspond to this, about the same kind of increase for MRR. Okay? And then we used 2 different versions of XGBoost. One that was like relatively easy, you can see all the parameters here, but it's not that regularized. And we have one that is extremely regularized. The difference in time is one takes about 4 hours to train. This one, I think it takes about 4 hours to train. This one takes like 1 or 2 days. And that's just regularization. If you think about XGBoost, you can actually regularize using lambda, L1 and L2 kind of regularization. So these are usually given by the lambda and alpha parameters of XGBoost. When you notice a huge gap between your validation curve and your training curve, that usually gives a space for regularizing in order to bring the 2 of them together. So every time that you have a large gap between validation and training, regularize more, move them closer to each other. So you may get a little bit more in generalizing, and you will lose a little bit in training. Okay, this is common, and this is basically what this regularization will be doing here. And
the 1 hour time is for just the validation test.
Sorry?
The 1 hour time is just for validation test.
The
runtime 1 hour.
No, that was for the training. So one, like the small model running 1 hour. Why did I thought it was for? Just 1 hour, and the other one 32 hours. Okay. And notice also that the difference in MRR is just in the 3rd decimal. So this is when you are competing in this kind of competitions, every decimal counts. Like it's really important that you try to optimize this the best. So like this was important for us. All overall, that wasn't the only thing that we used. Yes?
Oh, sorry, could you go back a little bit?
Yes.
Pretty bad eyesight, so maybe it could be key for people in the corner, like maybe the AUC, which one is higher, which one, like just like read it, I guess.
The second one is always higher, 92.54, and the first one is 92.38.
Okay.
How did you calculate it?
Sorry?
Sorry, if she said.
I didn't hear anyone.
Okay, could everyone here see that? Or? Okay. Carry on.
Okay, the difference is again is small, but like it works like a charm. Yes?
How did you calculate the AUC in this case?
Sorry?
How did you calculate the AUC?
It's calculated by XGBoost. It does it for you.
Okay.
It's an MRR should
it's
be.
AUC for each rank, for each item in the rank.
No, it's AUC overall.
For the
But for each item, not for each session.
Oh yeah, definitely. Because it doesn't make sense for each session.
Yeah.
Just what is that type or not? Is MRR is active? I thought MRR should.
That's about.
Oh, it's about okay. Sorry, guys.
Yeah.
My problem is when you have 25 ranks and there is only one click out on item, the problem is very unbalanced.
Yeah, that's why you have high AUC. But like it still is a proxy, it's like it doesn't really matter. As long as you increase the AUC, the MRR will increase, depending on the imbalance of the data set. No, we actually tried a little bit, but like it doesn't make a difference to us. Like it didn't make a difference. Like even though the data set was unbalanced, we didn't have any problem. Okay, any other question? Okay, so that wasn't the only thing that we tried. We tried a bunch of stuff, like a lot of stuff. I just spent a couple of months, more than a couple of months, just trying every single deep learning model that exists out there. You have no idea how many I tried. All in all, most of them failed miserably. Like, it was kind of funny because then we went to the conference in Copenhagen, and it was like the best paper is like, I don't remember the title exactly, but the moral was deep learning doesn't work really well for recommenders. These guys tried to replicate 70 different deep learning models for recommenders. They were able to replicate, I think, only 7. And all of them were in the same family of using autoencoders for recommender. Everything else they weren't able to replicate, and the authors will disappear or didn't contact or stuff like that. I strongly recommend that you read that paper. It's super interesting, especially to show that recommenders are still a hard problem, especially when it comes to production. Okay, so that being said, in the last part of the talk, I will talk about our deep learning approach, because there is one trick that allows us to use deep learning. And this trick actually works in a big generality, okay? So let's talk about what were the features that were more important. For me, so we were measuring importance in this case by something called the gain, that is by how much the feature is contributing to decrease the loss. That's what will be the gain in short. And most of the features, like I think the first 20 features already corresponds to 85% of the gain. With only I think the first 10 correspond to 79% of the gain. So most of the information are in these features.
You can start to run it with the 85 loss gain features?
We didn't, but it's really easy to do in the code. You can just go to the...
sorry.
Yeah. So one thing that is really surprising, and this is the part that I wanted to tell you. So the highest score here that we got was 67.98. If you were a 64, you were already in the first 20. The first model that one of us created was a rule-based model. No features whatsoever. It was rule-based. And it was doing 65. That was mind-blowing. And it was just he cleverly designed how to re-rank. And most of the times had to do with this. The most important feature is this item in position number 1? Or what is the position of this item? Basically, this is saying that Trivago is already doing a good job ranking these things. So we are piggybacking in what Trivago is doing in order to improve what they're doing. Okay? I mean, they spend a lot of time and money in doing this thing. So I'm pretty sure they have something that it works. So you just need to improve it. So you use what it works and add stuff. That's basically what this is. Position of item. Sorry?
If you have a feature, if the item is on the 3 spot, you order it also?
Say that again?
You ask about the first spot.
Yes.
Did you ask also about 3 spot, the 5
spot? Yeah. There are things in between. It's in the first group, it's in the first 3, that kind of stuff.
Yeah, it's also related to what you said about the mobile.
Yeah, exactly. So, another thing that was really important is notice how you could sort the items by price, because everybody cares about price, but everybody also cares about looks, or stars, or ratings. So you can also create a score associated to stars and ratings, and that was really helpful. That was one of the top features. Price ranker, as I was telling you before. So one huge predictor was also how much the user has interacted with that item. I mean, it's an indicative. If I'm looking at all the pictures, it's because I'm trying to convince myself not to pay that price, but the hotel looks really nice. So, and those were the top features. And before talking about deep learning, let's just take a small break. Okay, so actually I'm going to deviate a little bit from that, and I'm going to do a deep learning approach, okay? So, as I told you before, we try a lot of deep learning models, and all of them fail until we figure something extremely important. Most deep learning models could work as long as you give them the same features, But the difference is that you need to remember that deep learning models, they don't like weird stuff. They only like really small regions where everything works out nice. That means you need to normalize and treat your features. You need to pre-process your features, and if you pre-process them in the right way, you can just do almost as good as XGBoost. The difference is that you will have, the results will be, I'll talk more about that later. The results will be different in the kind of predictions. Let me go over there. So, we try many deep learning models. We start with a feed-forward neural network using the same features after everything, and that worked out well. But eventually, we try to use transformer. Why using transformer? Transformer is a unique architecture. It's one of the new architecture. It's a buzzword, and that was one of the reasons we use it. But the main reason is because it had the potential of doing something that any of the other architectures will then do, and it's local comparisons. If you look at how an attention head works, you will send all the information to the head, and the head is going to do comparison of all the different items, all again all. But it's going to learn what groups of items will be more relevant. It's going to understand which is the subgroups that have more correlations among themselves, and use that subgroup information to boost the signal up. So if we were able to capture that, we will be gold. And we find out that to some extent it does. So let me go over how that works. So this is the general architecture. I'm going to explain each of the parts and how we went over it. So the first thing is we need to put the data in. So to put the data in, we have three kinds of data. XGBoost doesn't care about the kind of data, so XGBoost is magic because of that. But deep learning needs, you need to distinguish between what is a categorical feature, a numerical feature, and an ordinal feature. All of them are different. Like they have different meanings for us. For the numerical features, and as all of them are different, we need to use different kind of embeddings for each of them. So for the categorical features, that is easy. We have done it in NLP since the old times. You just, for every different category, you associate a vector, and then you let the vector representation be learned. That one is easy. That's not a big problem. For the ordinal features, you can treat, as long as you don't have many ordinals, you can treat each ordinal feature as a category. And that's sort of what we did. There are other tricks that you can do, like positional embedding kind of tricks that to treat, like to have some relative order between them. We didn't try many of that, and the only change that we make is for some negative ordinals that we have, we just put the sign there and treat it as positive. It wasn't a lot. But the one that is interesting and the one that you should learn for every deep learning model that you're going to use is this one. You look at the distribution and you use a power transform in order to have whatever distribution that is usually tail into a more normal-like distribution. So the power transform is basically, you are going to put things between 0 and 1. You normalize it to 0, 1. Then you use a particular power in order to have that power make the distribution more normal-like, and then you put the mean at 0. That's basically what a power transform does. Luckily for us, we don't have to do that by hand. There is something called the Yeo-Johnson transform that will do that in a better way. Same idea, but in a better, almost same idea, in a better way and much faster. And there is a this can be done in scikit-learn. So you can do.
You started the data engineering in Java and then you moved to Python?
Yeah. At least for this part, yes.
All the deep learning was in Python?
Yeah, all deep learning was in Python because I try and I fail to use MXNet. There's people who are really proficient at it, but like I found it particularly troublesome sometimes, especially debugging or installing or playing with it or building anything. Anyway, I don't like it. So you have so this transformation will allow the deep learning models to capture the relevant information. This was the thing that way from deep learning is not working to deep learning is actually working. It was just this thing. So once we have this, we could begin iterating, try different models, we try LSTMs, we try transformers, we try.
But our LSTM, what was the sequence in LSTM?
25 things. You can think, again, if you're thinking in scrolling, you're basically thinking in a temporal movement. You're going from 1 to 25. So that's a sequence. So you can think each thing.
So it was the level to level?
It was the sessions, basically.
25
items in a session.
Yeah, but
so first item goes to the first thing of the LSTM, second item goes to the second thing of the LSTM, third item.
And the level is a click out on the end.
There's, you mean up here?
Yeah, the click out on the end.
Yeah, sure. Well, like they click out for each of them.
It was a binary.
For the binary.
It was binary before, and now it's the level.
No, the system will be binary. We will see that in the loss function here in a second.
Okay,
so.
One quick question. What is the transformation that you use? What are the
Geo Johnson.
Okay. And then Geo Johnson does it automatically for you. But what is the power transform that converts the red to blue?
It does actually. It's incorrect in Geo Johnson. Like you can do that by hand, finding the right exponent, but like Geo Johnson will, you need to train in the distribution of the data.
You usually do it in regression. This is what you once did in regression.
So how many numerical features did you have? Just roughly, I guess, 100?
200, something like that.
So did you transform each individual feature separately, independent of all the other ones?
Yep.
And is that also true for categorical and ordinal features? Yep. So you went through 300 features one by one.
Yep. Yeah, I still remember the pain. Okay, so after you have that, there is one more feature that was a trick that we learned from a Facebook paper that was extremely interesting for us. So we have this so we already trained the SGBoost. The SGBoost was really good. We wanted actually to get some of the information that the SGBoost is able to get. So if you think each of the leaves of the SGBoost as a 1-0 kind of thing, every result, once you look at the different trees of the SGBoost and you look at which leaves had been chosen, you obtain a really, really sparse vector of zeros and ones, right? It's the leaf that was chosen, like if the depth of the tree is 10, then there will be 1024 leaves, and only one of them will be chosen for every tree. If you are training for 500 rounds, then you have 500 times 1024 number, like a sparse vector of zeros and ones, right? You can actually, for each item, have that as your prediction. So it's a really sparse vector, and you have this for every single item. So you have something that is like millions by at least, I think, 1 million as well or something like that. So it's a huge sparse matrix. Now, you can take that really huge sparse matrix and use single value decomposition. As this is a sparse matrix single value decomposition, you need to use sparse single value decomposition, and you need a lot of computing power to do this. So we did a computing power computation, and we appended, like we reduced that thing to 100 dimensions, and we append that to the embedding, and we just treat that as it is. We didn't process it, we just treat it as it is, and we added as features to each of them. This is a really cool trick that I found it helps, and it has helped in other situations. Yes?
So each leaf is an item?
No. So you have an item, and the SGBoost is going to predict yes or no, right? But before it predicts yes or not, it needs to go over every single tree on the SGBoost. Every single tree on the SGBoost will have a leaf associated to it that is the leaf that decided, right? So there are, for every tree, there are 1,024 different leaves. So I'm going to choose to put 1 to the leaf associated to the prediction in the tree and 0 for all the others. And I'm going to do that for the 500 trees that I have. So I have a really 1024 by 500 by millions matrix.
Facebook did it?
Huh?
Facebook did it?
They sort of have it hidden in one of their papers. Yeah. But like we use it, and we actually, it was one of those cool things that you do every now and then, where you rent an EC2 instance that is just like CPUs. And I was using at some point, I think it was 4 terabytes of RAM. And that was like, you could see, and all the processes running at the same time. It was beautiful. It was one of those things that Jesus Christ.
How much was that cost?
I cannot tell you, but I can tell you I wasn't paying. So that was fun. That was tons of fun. He actually ran for. I mean, the SVD part didn't take that long, but like some processing that needs to be done before and after, I think it took like 2 days to run. Yeah.
Do you have any intuition on why that works so well?
Yeah, definitely. So the best intuition that I can give is like the choices of leaves. The SVD will just learn co-occurrences, right? Kind of thing. So for things that have the same kind of co-occurrences in the different trees, they're basically saying that they are similar. So basically saying this item within this session, within this context, is similar to this other item because they are producing almost the same trees in the SG books. So that thing can be captured by the SVD.
Right, so what you did here is just to replace the decision process of the XG boost with neural network.
No.
If you took each leaf of the tree and the XG boost decide among all the tree what is the decision in the end.
Yes.
This is the decision process.
Yes.
What you took one step before the decision process,
Yes.
every leaf, and insert it to a neural network.
Yes.
So the decision there, the decision was made now in the neural network.
Yes, but it's not replacing the neural network. It's not
No, replace the decision in the XG boost. The decision process, never mind.
Not really, right? Because it's only picking, like you don't know what the tree is. You're just picking the different items that correspond to the same thing in the tree. Which you kind of learn something about the items.
So yes and no, like both of you are right, but like there is a thing like is the decision is not totally. It's a noisy decision because if you have the sparse vector, then I will agree that it's the decision. The SVD is just telling you how they compare as the decisions of the SG boost. And this was just to augment the quality of our deep learning model because even without this, they were performing quite well.
You could run, let's forget about SVD, you could run PCA to take some information from the balance and insert to the neural network. It's also a decision.
PCA does SVD.
I know. So talking about the embedding level of the PCA.
So you're technically, right, you're using the XG boost, like
the information of the XG boost to make a decision.
Yeah.
But then you're using it as a part of the input for that decision. So what I think what Felipe is saying is now you're not aligning it fully, you're just having it as some sort of bias towards
but it's I think it's very good idea.
Facebook had really good idea there. It worked out for us. I mean, again, like this was able to, like the deep learning models were performing well, but we wanted to be as close as possible to the SG boost model. So when we do an ensemble, then they will be, like if you have comparable results, then usually boost. If you have one that is overwhelming over the other one, it's much more difficult to have a nice boost. Also, you need to have like some sort of orthogonal kind of results. Deep learning is really good at obtaining kind of information that SG boost can't. So usually SG boost and deep learning, they ensemble really, really good. So like if you are participating in a competition or you just want to increase the scores, combine SG boost with deep learning. They boost performance quite well. So, okay.
Why didn't insert the rule-based model?
Why what?
To the ensemble. Why didn't insert the rule-based model?
The rule-based model.
The rule-based.
Talking about before.
Oh! Yeah, we didn't. I didn't talk about that. That would have been interesting. Okay, yeah, we didn't talk about that. Okay, now the attention layer. So the attention layer, as I tell you, like the information of the items is now transferring 25 different items. But when you look at what parts of the items is attending, you notice these groups. And these groups are always really kind of well behaved. Like notice here is saying like, oh, this head basically for this subset of items wants to compare the first 6 items because those items may be similar. So I want to pay attention to them and see like if that actually like I want to pay attention to them because I want to distinguish between them. So the intuition that we have that there will be subgroups that the attention heads will detect that will help doing the predictions actually happens when you analyze the attention heads. So our hypothesis was true. That's the only thing that I'm saying. It does select the right subgroups. So then for the feed-forward part, we just put the usual feed-forward. There's something that I'm hiding that I will go back. So there is a feed-forward part that is just the results, you pass them through a feed-forward network. See? But in part of that is because if you look at the original thing, in the embedding, we actually separated the things that are completely session from the things that are only item-based. The item-based that go to the transformer, but the session-based ones, we just concatenate them at the end. And that's why you need the feed-forward, because you want to mix those two kinds of information. Make sense? So, and then the loss function, we just use the same loss function we were using, like binary logistic function, to each of the items, and that goes back to your question. At the end, the last layer, you will have a loss function here, a loss function here, a loss function here.
Yeah, it's level to level.
Yes, and item to item, I would say.
Item to item, level to level.
So for each item, I'm still predicting if it is 0 or 1, if it was predicted.
You started from the lowest rank to the highest rank.
Yes, this is lowest rank to highest rank, yes. Okay. Then we see the transformer actually by itself did 6734, and with SVD it does 67, with the leaf streak it does 6765. So the gain was 3 points in the third decimal, which for this competition is a lot. But these two combined also give a almost 3 points boost, the transformer and the gradient boosting, to the overall result. And that actually is significant for us. It was really hard to get. Like, it was a lot of work. It was tons of fun, but it was a lot.
How much time do you work on this competition?
4 months.
4 months?
Yes.
Full of months from the data till...
No, 4 months working all the time only on this.
Yeah.
My job during 4 months was just this. Actually, our team's job for 4 months was just this. So actually, let me tell you a little bit about what we do. So Layer 6 is a company that works in 3 areas: research, competitions, and production. So we do research, we publish papers, not only competition papers, but actually like papers. Right now, a group of us is giving some talks in Korea, having fun, and also having fun here. We also participate in competitions, image competitions, recommender competitions, general Kaggle competitions. This is about 60% of our job, and the last part of our job is production. We help increase the value for TD by tackling some of the most difficult use cases that you can see that TD use. And that's 30% of our job. And we like taking pictures with our bottle all around the world. And I think that's it. Thank you. I don't know how to answer to that. So we have a picture of the bottle with the cup of the MBA. That being said, the cup is super small around here, and this is the
Okay, we do have like 2 questions from online.
Okay.
That are more from like the before, but we'll just ask them
Yeah.
here. So the first one is, so in the data, why would the second rank have 0.5? If someone Googles something, sometimes they wouldn't click on the first thing.
Say that again.
Does that happen in your data set? So they are saying that some people's habits are to not click on the first
Yeah, that's perfectly fine. That doesn't matter. That doesn't mean that the being first is not an important feature. It's that in that particular case, it wasn't that important.
Okay, and I hope that they're okay. The other question is, how did you deal with the clickouts that are not the last ones?
We only used it for feature generation. We really didn't do anything else. I know some other teams, they use them to augment the training data set. We didn't do that.
Okay, floor is open to ask any sort of...
So before that, like I want to say, like we ranked second in this competition. you should, like, if you have the time, go through the code of the first place. Logic AI did an amazing job doing participating in the competition, and so did the other teams. All of the solutions are in the GitHub, or the code are in the GitHub. If you want to learn how to do these things or how to create features, go through those codes, go through our code. They are really good, and they have similar but always different ideas, different approaches, and you can learn a lot out of that. Yes?
Ever seen the data that someone would like click 5 things in a row really quickly and open
Yes.
multiple tabs and stuff like that?
Actually, that was at some point one of the features, and for the rule base, one of the rules is if they are clicking 1, 2, 3, 4, then predict that it's going to click 6. So like there were many like that, and you can encode that. Like for example, one of the features that we had at some point, I don't know if it came to the 330, was you can measure the how do you call this, the delta on the click out, like what is the direction that is moving. So yes.
Did the device actually seem to matter? Like I can see that in the field. Because you had all these.
I think we had it, but I don't think it mattered. That being said, in some data analysis that we did, like when we did some sort of separation to try to use, so there was. So SGBoost, like once you put like a categorical feature, SGBoost will try, it needs to make the decision if this categorical feature is important or not for the decision. Sometimes it won't pick it, but you can force it to pick it. How do you force it? You take your data, you split in the category, and for each of the pieces of the data, you train an SGBoost on it. So you are forcing this thing to pick the device. So we tried doing that with 2 of the features. One was the country, and the other one was the device. And then we tried to merge the results back in, but we didn't get any boost. But like the behavior in each of the different devices and each of the different countries was actually different. Like the SGBoost will have a huge variance depending on the country. That was shocking because we couldn't capture anything out of it. Yeah.
Question is, do you know what algorithm the winning team used, and perhaps what might have been different?
So I know that you can find the paper in the RecSys webpage, and I know that they use, so their approach also, there is a particular kind of boosting technique called DART that is also heavy regularized, and I know they use that in order to, with the features they created. So they have another set of features that they created, and then they use DART to that. Yes.
2 questions. Question 1 is, I know for recommendation systems, deep learning is not the go-to solution.
Yep.
But in this case, you transformed it to a classification problem. And in that case, deep learning is a good solution. In many cases.
So yeah, go ahead.
So then, and I also remember that in the middle of the talk, you said the transformative feature was a step that really enabled deep learning. Isn't this common practice in deep learning to do feature transformation normalization?
So yes and no. So like if you think, for example, in images or NLP, how much feature transformation are you doing? Like the goal of deep learning or the dream of deep learning is an end-to-end solutions when you don't have to do feature engineering.
Exactly.
But that's the holy grail. It hasn't happened.
Well, like, for sometimes even in images, you do like, batch normalizations, even in steps in hidden layers.
But those are architectural designs in order usually to decrease how the signal is being passed through the network. Right. So it's not that much about the data, but about like how the signal goes through the network.
Correct, but what I'm thinking here is that this is a standard practice in deep learning. Why did the transformation here was a novel step?
I'm not saying that it was a novel step. It was the step that let us do stuff. Like for example, if we try first with normalization, it wasn't particularly good. We tried with techniques that were like, it wasn't that much the normalization, but the kind of normalization. We really needed to put it in this normal way instead of just centering and dividing by the standard deviation. So, and the feature generation was kind of really important.
Yeah.
But like, my claim about deep learning is most about end-to-end solutions. Like most of these things, they claim that they have an end-to-end solution, and they usually don't work. And that's sort of what we want, because you will have made that really, really nice paper.
One thing I'm curious about, so in the setup, you're training on everything up before the final action, and then predicting the final action. If you're thinking about putting something like this into production, that setup kind of seems as though every time a user does some action, you'd be producing a new set of predictions and almost changing the interface, which sounds like a terrible experience. So I'm wondering, how would you think about?
So that's a really good question, and we were asked the same question in the conference. I don't think it was answered.
Sorry.
Yeah.
The question is why the result not refreshing?
You get very fresh results every time you change you click on an item, you get totally different kind of recommendations now.
Here, you ask why it didn't refresh, why they don't refresh the result, why you need to re-render.
I'm wondering if you were implementing it in production, whether you would actually refresh the results after every action, or how would you think about the frequency that it makes sense to refresh?
So it only makes sense after every action, because most, if not all of the session-based recommendations so far, they don't use the user history.
No, he's right. Like if you were going to use this, like you will have
every action, not
yes.
every session. Right?
It's not
right, every action.
Yeah.
I agree. Like I don't have like something that is sometimes like machine learning or these competitions. It's not that much about like how to put it in production, but about something more important. What things were the important features that you can use to put in production. In this case, we found out that like if you look at all the teams have different ideas, different approaches, most of them really good. So you can take the features that each of the team created and see if they work for different use cases that you have. You just append it to whatever collection of features you have. And then you have a bank of features that you can use to predict other things.
And you also don't know really what is the session, what is the search. They tell you this is the session, this is the clicks, and this is the outcome. They're limited for their production. You don't know what is the production behind this competition.
So you emphasize a lot on feature engineering, and you guys put in tons of effort on doing feature engineering. So for our learning purpose, like what's your learnings from the feature engineering, and what are some of your go-to methods where you will start on right away when you have a data set?
Yeah, I was asked that question during the break, and that's a good question. So I will give you two things. Like the most important thing is like try to think as a user and try from how you are thinking and interacting with the product as a user. Come up with features that you can then translate to code. That's the most important part, and that's where creativity plays a huge role. Once you are able to do that and extract many things, there are many techniques once you have those features. You can think about features generated from the distributions associated to those features and use those distributions, like get the mean, the median, the standard deviation, whatever, max, mean, all these key. And for every feature that you came at by thinking, you can create maybe 10 new features, how they relate with other features and that kind of stuff. And then you have, that's how the number of features grows really, really fast. Yeah.
And for each session, there would be a possibility of certain events happening or not happening. For example, somebody sorted, not sorted, somebody clicked on something, all that stuff, right? So you had one hot encoding for each kind of activity. Is it like that, or?
No, we have like you can. I think there were in total 11 actions, possible actions that you can do, 10 or 11. We do hard encoded that at some point and use it as a feature, or not like that, but like more like how many of these actions were there, how many picture interactions, how many deals interactions, how many filtering, how many, that kind of stuff. So you summarize.
Oh, you summarize it. Fine.
Could you add information, external information to the problem? Were you allowed to do?
We weren't allowed, but we tried. I mean, we never submitted with the extra information, but we wanted to see if there were things that were relevant. So, and actually another team did the same. They gave a talk about like how important it was, but like it was difficult. Like for example, one thing that we tried to capture using external kind of data set is like you have the city, and the city usually has some geographic coordinates. So we tried to put that there in order to adjust for the time zone, because like this was universal time and we wanted to have local time, but we didn't got anything out of it.
How was it doing on shorter contextual, shorter sessions?
So actually shorter sessions, they have a huge correlation with item 1. Another thing, like you should also realize that the features that we built are non-unique, in the sense that what the model finds is that these features correlate really well to each other with the outcome. Other set of features like that may work for other team may not work for us, and our features may not work for them. The reason is because the model is designed to find the patterns within these features and correlate them between them. But when you put them against some new features, actually the score may decrease because it's not able to find the same patterns. So like sometimes that in production means that you need to start from scratch.
Does anyone who hasn't asked a question want to ask a question? Now it's time.
Yeah, the thing about normalize this context cumulative gain, why they didn't use that measurement.
Say that again?
Why they didn't use the measurement for the
I think their business model is more about like the last click out, and that's the last thing. That's the kind of thing that they can measure. If you click 1, 5, and 7, like it's difficult to measure this, to have this measure, because you don't know if does that mean that I had a good ranking for the users that I can use the normalized cumulative gain or not. Like it becomes tricky to assess if that was the ground truth. It basically is a problem of ground truth. Like how do you go about what is the ground truth for this order? So I think that may be the reason. Maybe also the business model. Mm-hmm. I honestly don't have a better answer than that.
Is there any unstructured features in the data set, like maybe not the metadata, the images, but any sometimes you choose to tell based on the images. Did you have access to the images, or did you try?
No, we didn't. It would have been extremely fun, because one of the features that I tried to create at some point and it didn't work was a beauty feature. So the beauty feature was, I will think that a hotel was more beautiful than another hotel if people spend more time looking at the pictures. It didn't help.
I'm just wondering, did you have access to the test set predictions for other teams at all? Because I was wondering if ensembling maybe predictions from different teams' models could improve it, or are they kind of all getting the same examples?
I'm pretty sure if you take the top 5 teams and you create a model on top of those results, you will get much better results. I mean, it's usually because like there will be some degree of orthogonality between the features that are created. So like the teams, like some models may be really good to learn certain patterns that the other one can, and vice versa. So like when you ensemble those things and it becomes better. Actually, I didn't say something that maybe I should have mentioned. In our ensemble, we actually trained many models, and in total we have, I think it was like 25 models, and all of them were combined, and there were some XGBoost and some deep learning. And as there were several people in our team, each of us have a relatively different approach. What we find out at the end is that all of our models contributed to something for the ensemble. Like it was pretty cool, because like you've been working in this for a long while and you felt that you actually put something towards the end result. And it was a team effort, like it was pretty cool, and yeah, we enjoyed it a lot.
About the external data, something bothered me. Did you add in Trivago? It's a site that directs to other site.
Yeah.
Did you add information which site is going to direct to?
We don't have access to that information.
Can you give it from external data?
I don't think you can get it. Not as of this. I don't see how, even with a web
There is
scrapper.
no
like
link or something that can in the data that
no.
link of the site.
But then on this, continuing on the same line, when somebody actually books, then there must be some communication happening with the data.
I'm pretty sure they do have access to the data. It's just that we don't.
Actually, you said you use word embedding, regular word embedding for the categorical data, right?
Yeah.
And for example, you showed us one feature which was a description about that hotel, I don't know, pool, something like that. So there are a couple of words there. There's just now one categorical word over there. How did you combine all of these, like?
So it was in total, I think, 120 different words. That is actually the property. So you can just hot encode that. It's just 120 different words.
Okay.
So it's just.
How do you combine? Is it just gonna be one categorical?
You can create one per word, or you can summarize it in the total number of words. We tried all of these variations.
Okay.
Like we actually did a study of the relevance of the different properties associated to each of the hotels, and because like the vector, if it's 120, it's a 120 dimensional vector, one hot encoded, so we added a lot of features, and we didn't want, it will just make the model longer to train, so we tried to compress it using SVD or things like that. We weren't able to gain, like eventually we ended up doing a study, and we find out that when all these things are put together, most of them contribute the same. So like if you wanted to keep it, you needed to keep them all.